Thank you very much, Jonas, for the kind introduction and for inviting me to give this talk. So yes, I will talk about this joint work with Akima Bessaih, Benedetta Ferrario, and Landoulsi, where we address the problem of continuous data assimilation for the two-dimensional stochastic Navier-Stokes equation. So I would like to start by briefly recalling what the data assimilation algorithm is. Then I will consider the deterministic case, and then I will switch to the stochastic case presenting our results. So just to begin, what is the data assimilation algorithm? So what is the idea behind this kind of algorithm? So the idea is as follows. Suppose that you have a state variable, u, that represents the physical reality of your system at time t. And you know that this quantity satisfies a suitable evolution equation. So for instance, you have an equation of this type where f represents the dynamic of your system. And usually, or at least in this talk, you're supposed to have a dissipative dynamical system, okay? So what happened in the concrete situation is that you know the equation that govern your physical reality, but usually you do not know exactly what is the initial condition of your state. So in principle, if you know the initial condition and you know what is the equation for your state variable u, you are able to predict the state of the system at any future time t. But if you do not know the initial condition, you do not know how to make a prediction. So the problem is try to understand what is a good approximation of your initial state. And in order to do that, you can just observe the physical reality. So you can make some observational measurement that I will denote with this operator R of h of u of t, and I will explain more in details what is this operator R of h. But for at the moment, just think about this operator as the observational measurements that you can make over a sufficiently large time interval. So you can observe the reality, and usually this number here, h, represent the spatial resolution of your observations. So what is the idea? The idea is that given the observational measurements for a sufficiently large time, you are able to construct an increasingly accurate initial condition for your state u, and so when you know the initial condition, you then can make prediction for future time. So the problem is, given the observational measurements, try to reconstruct accurately the initial condition of your state system. How can you do that? The idea is to use this data assimilation algorithm. So the idea is to introduce a suitable approximation for your equation. So you introduce another equation satisfied by a state variable v that evolves from an arbitrary initial condition. Okay, so for instance, just think about the initial condition of this new system as to be 0, for instance. And how to construct this approximation. So the idea is that the dynamics of this approximation is driven both by the model and by the observational data. So the equation that you construct has this form here. You see that the evolution of v is the same of your original system. But then you also add this term here, and what is the role of this term here? Basically, you see that on the spatial resolution h, you are forcing the approximation to agree with the true solution. So the idea is that you collect your measurements and you continuously insert your measurements into the system, and you force the approximation to agree with these observations. And in front of this term, you have a parameter mu, which is called the nudging parameter, and somehow represents the speed of convergence of this approximation. And as I said before, h is the spatial resolution of your measurements. So, in other words, what is the effect of this term, which is called usually nudging term? The effect of this term is to act on the quartz spatial scales and enforcing the agreement with the observations. And somehow we will see at the end of the talk that this is enough. So it is enough somehow to force the dynamics on the quartz spatial scales because you are considering a dissipative system. And so the dissipative part of the equation makes the rest in the sense that the dissipation effect ensure to control also the fine scales. Okay, so if you consider this kind of perturbation here in your evolution equation, what you expect and what you actually prove is that you have a synchronization between the approximating solution V and the true solution U. So you have that when times goes to infinity, the solution of the approximating equation converges to the solution of the true system if you, and we will see this in more details, choose suitable the parameters mu and h. So this means basically that if you wait enough time, then the solution of this approximation will approximate the true solution of your system, and so you can use this, let's say, this data as your initial data for the true dynamics, and you can make a prediction in future time. So this is, roughly speaking, the idea of the data assimilation algorithm. And now I will like to recall the paper by Aswani also and Titi, where the author improved this kind of algorithm for the deterministic incompressible two-dimensional Navier-Stokes equation. And basically, this is the starting point for our work since we, let's say, extend their results to the stochastic setting. So, in this paper, the author considered the two-dimensional Navier-Stokes equation. So, what is the motivation? Basically, if you look at the motivation for studying this kind of data assimilation algorithm, you see that there are application in weather prediction. Okay, so in an old paper by this author here, they actually show not rigorously, but they show that if you combine some observation with the true dynamics of your system, then you are able to make prediction at future time, which is exactly the idea of data assimilation. And somehow, Advani also and Titi formalized this idea by considering the two-dimensional incompressible Navier-Stokes equation, which is not exactly the model that you use for weather prediction, but somehow it's related, and in particular, it is analytically tractable, so you have well-posedness of this equation, and so you can implement formally this data assimilation algorithm. So they consider the two-dimensional incompressible Navier-Stokes equation that I briefly recall here. So I recall that the Navier-Stokes equation describes the evolution in time of the velocity vector field. So we consider the two-dimensional case, we suppose to be in a bounded smooth domain, and we consider Dirichlet boundary condition. So this is the equation for the velocity vector field U. You have the Laplacian term, which is the dissipation in this case. And this parameter here will play a role in the following. So nu is the viscosity coefficient and represent the intensity of dissipation. Here you have the transport term, P is the pressure, and you also consider a deterministic forcing term, F. So in their paper, the author consider a time-dependent forcing term. Here, for simplicity, I will just consider a time-independent forcing term. And so we consider this kind of the equation under the incompressibility condition. And so in this case, when you want to formally analyze this kind of equation, usually you project them into the space H, which is the L2 space with the divergence-free condition, and you also consider directly boundary condition. So projecting every term into this divergence-free space, you can write down your equation in the abstract form. So the operator A is the projection of minus Laplacian. This term here represents the projection of the nonlinear term. And working under this assumption here, divergence-free, the divergence-free makes this term, the pressure term, disappears. Okay, so these are the deterministic Navier-Stokes equation written in the abstract form. And as I said before, what is our aim? Our aim is to make prediction at future time. And the problem is that we do not know exactly which is the initial condition of our system. Okay. So in order to try to recover in an accurate way the initial condition, we introduce the modified equation, so the nudging equation, which is exactly the Navier-Stokes equation perturbed by this term here, which is the nudging term. And as I said before, what is the effect of this term is exactly to force V to go towards U on, let's say, at a coarse spatial scales. So in front of this difference, there is these operators that I will explain in a moment. And as I said before, when you consider this modification, you can take any initial condition, okay? So more formally, what is this interpolant operator RH here? So this is a linear operator that goes from the H1 space to the L2 space and satisfy a suitable interpolant inequality that reads as follows. So you take any function phi in H1 and you have that phi minus RH of phi L2 square has to be bounded by a constant times H square the H1 norm of phi to the square. Okay, so this is, let's say, the abstract form of the linear interpolant operator, but you have different concrete examples of this operator. So the first example that you usually use in practice is the so-called finite volume. So what is the idea? The idea is that you have your domain D, okay? You divide your domain into some squares Qj such that the diameter of this Qj has to be at most of length h. And so your domain D is the union of these pieces here. And how does this interpolant operator act on a function phi? Basically, you consider the mean value of phi inside of every square, and then you take the sum of all these mean values. So what is the idea? The idea is what happens in practice. When you do observation, you do not have the exact observation of your state at any point in space, but you have some mean values. And the accuracy of your observation is related to how big or how small is this this number h, which somehow represent exactly the diameter of your square. Okay, so this finite volume is what you expect to observe in practice. So in practice, you observe some mean values, and what the data assimilation algorithm says somehow is that this is enough to recover all the informations. So this is the example more related to the reality. But there is another example which is quite common in the mathematical literature, which is the Fourier projection. So as another example of your interpolant operator RH, you can consider exactly the projection on the modes, such that, let's say, on the modes, okay, let's say that you can consider as an example the projection on a subspace of dimension k, okay, let's say, so basically k is related to the k eigenvalue of the Laplacian operator in this case, and so you have, let's say, a relation of this type here. So lambda k, which goes last like k to the square, is more or less equal to 1 over h to the square. And in this case, how does the interpolant inequality reads? So in this case, if you consider phi minus the projection k of phi, which is phi minus the projection on the low modes, it's exactly the projection on the high modes. And the interpolation inequality in this case reads in this form here, but it is exactly the inverse Poincare inequality that you have on bounded domains. So let's say a typical example that you find very often in the mathematical literature for this kind of linear operator here is given by projection on the low modes, and this interpolant inequality is nothing but a generalized inverse Poincare inequality. Okay, so what is the result proven in the paper by Aswani also and Titi? They prove this result here. So they consider a suitable forcing term that belongs to H and consider a interpolant operator that satisfies the interpolant inequality that I just commented. And they prove that if you consider the solution of the Navier-Stokes equation starting from an initial condition U0, and you consider the solution of the nudging equation starting from an arbitrary initial data in H, then under suitable assumption on the parameter mu and H, basically you have that when times goes to infinity, the approximating solution converges to the true solution exponentially fast in time. And what are the conditions on the parameter? Basically, you see that the condition that mu and h has to satisfy are these. So let's say h has to be sufficiently small, so it means that the spatial resolution has to be sufficiently small, okay, and mu has to be sufficiently large, and both the parameters are related to the let's say, to the parameters appearing in the Navier-Stokes equation. So you see that here appears the intensity of the forcing term, here appears the viscosity parameter, and lambda 1 is the first eigenvalue of the Laplacian, so it means that you also have a dependence on the domain. Okay, so if mu and h satisfies this kind of condition here, basically you prove that the solution of the nudging equation when times goes to infinity, so for a suitable time suitably large, is a good approximation of your true solution. Okay, so you can approximate the true solution with this modified equation. So this is what happened in the deterministic setting. And now let us come to our results. So we consider a stochastic version of the Navier-Stokes equation. And so we prove that this kind of data assimilation algorithm work also in this setting. So what is the idea? The idea is that since you cannot predict exactly the reality, it makes more sense to consider equation driven by some random perturbations. So it makes sense to consider the stochastic version of the Navier-Stokes equation. And this is what we consider. So we introduce a probability space, and on this we consider a stochastic perturbation, which is of this form here. So W is a cylindrical linear process with values in some separable Hilbert space U, and G is an operator which is Hilbert-Schmidt from the space U, where the noise lives, and the space H, where the solution is. So this is the stochastic counterpart of the Navier-Stokes equation, written in the abstract form, and also in our case, we suppose that we do not know the initial condition, and the aim is again to make prediction at future time. So the aim is to try to approximate the true initial state. Okay, so for simplicity in this talk, I will consider a noise of this form, namely an additive noise. So you see that the operator G does not depend on the solution itself, so it is an additive noise, just for the sake of exposition. But in our paper, actually, we consider the more general case where the operator G depends on the solution, so you are in the so-called multiplicative noise case. So starting from this equation, we consider again its nudging modification. So we consider the Navier-Stokes equation, stochastic version, and we again perturb this equation by this nudging term. And the initial condition also in this case is arbitrary. So our result reads as follows. So we suppose to have again an interpolant operator that satisfies the interpolant inequality. U is the solution to the Navier-Stokes equation, stochastic version, and V is the solution to the modified nudging equation. So also in this case, if mu and H satisfies suitable condition, then we again are able to prove that the solution to the approximating system converges to the solution of the true system when times goes to infinity, also in our case exponentially fast, and our results holds P almost surely. So for almost every trajectory we have this kind of convergence, and we also can prove that the condition, the convergence holds in expectation. So what are the conditions on the parameters in this case? So we have exactly this condition here that appears also in the paper by Azuani, also and Titi. So also in our case, it means that H has to be suitable small, so the spatial resolution has to be suitable small, and mu has to be suitably large, and you see the difference with the Azuani, also and Titi is this term here. So roughly speaking, if you consider a stochastic perturbation, a stochastic force into your system, then somehow the intensity of the stochastic forcing appears, and the nudging parameter has to be greater than the sum of the deterministic force and the stochastic forcing terms. So roughly speaking, if you switch off the noise, this term here disappears, and you recover exactly the deterministic result by Azuani, also and Titi. What about the proof? I will just briefly give an idea of the proof of this result. So what is the idea? So as I said here, you want to prove that when times goes to infinity, the solution of the approximating system converges to the solution of the true system. So what you want to study somehow is the evolution in time of the difference between these two solutions, and prove that this goes to zero exponentially fast. So the first thing to do is to introduce exactly the difference of V and U. So you call R this difference, and you study the evolution in time of this difference here. So if you write down the equation satisfied by the difference, you see that you obtain an equation which is deterministic. So since the noise is additive, when you consider the difference between V and U, the noise disappears. So basically the equation for the difference is deterministic, and this means that you can perform a pathwise analysis. So in this case, all the results that we obtain are pathwise results. So once you have the equation for the evolution of the difference, you take the scalar product with R, and by standard arguments, you are able to obtain an equation for the H norm to the square of the difference. So these are classical estimates that you do in the Navier-Stokes equation. But what is the crucial point? The crucial point is that when you obtain the difference, the terms, the nonlinear term coming from the difference of the two solutions, you obtain this term here, which is standard estimates for the Navier-Stokes equation, but then you have to deal with the term coming from this nudging parameter here. And here, when you do the estimates, you see that you obtain a term that involves exactly the interpolant inequality that I told you before. So basically, here you use the interpolant inequality that I stated before, and writing down the equation satisfied by the difference, you obtain this kind of equation here. So basically, you have the evolution of the H norm, okay? So the idea is just keep the terms involving the H norm. So the terms involving the V norm, you can neglect it if you assume that this term is positive, and this is exactly the first assumption that we make on the parameters mu and H. So under this assumption here, you basically can neglect the term involving the H1 norm of the difference. And so under this assumption, you obtain an equality of this type here, okay? So by the ground-1 lemma, you're able to estimate the difference of U and V to the square in the L2 norm in terms of this exponential here. So you see that you have the exponential of minus t times mu plus 1 over nu over t integral from 0 to t of the H1 norm of the solution. So what is the idea at this point? So the idea is you want to prove that this term converges to 0. This term is bounded by the exponential of minus t times something. So the idea is that if this term is positive, then you have exponential of minus something that will converge to 0 exponentially fast. So the idea at this point is try to estimate this term here and make suitable assumption on the nudging parameter mu such that this term is greater than this term here. So the second step at this point is to obtain suitable estimates on the H1 norm of the solution of the Navier-Stokes equation.
Excuse me. Excuse me. Is there a typo? There should be a minus, maybe?
Minus where? Sorry.
So in the line before, you have mu minus 1 over nu, and then the norm.
Yeah. Sorry. Yeah. There's a typo. Yeah.
Okay. So in the last line should be mu minus.
Yeah, exactly. Yeah.
Great.
Yeah. Thanks. Exactly. Okay. So the idea is to estimate this term here. And so you can do that by exploiting the exponential martingale inequality. So using this tool, also this is quite classical, you can obtain an estimate for the supine time of, let's say, the relevant norms of your equation. So I will skip all the computation, but at the end you obtain an estimate of this type here. So it's an estimate in terms of a parameter R. And what you really need is to control this term here. Okay, so basically, if you divide both terms of this inequality by 2 over n squared t, you obtain exactly the term that you wanted to estimate, and you obtain that this term is estimated in terms of the forcing terms and something that depends on the parameter r and the initial data. This estimates holds for any time, and the probability that this estimates holds true is 1 minus something that decays exponentially with respect to the parameter r. So, since this estimates holds for any time, you can take the lim sup. So, when you take the lim sup when times goes to infinity, this term here disappears. And basically, what you obtain is that the probability that the lim sup of the term you are interested in is bounded by the forcing term. And since r is arbitrary, you can take r sufficiently large such that the probability of this event is equal to 1. So what you proved basically is that with almost surely, when times goes to infinity, you have a control of the growth of the H1 norm of the solution, and you control this term in terms exactly of the forcing terms that appears in your equation, so the deterministic forcing term and the stochastic forcing term. So what we obtained so far, I just, so there is the same typo here. Okay, so basically, you prove a pathwise estimates for the difference of the Navier-Stokes equation U and the nudged equation V. So you have an estimate of the difference in terms of the exponential of this quantity here. And you have this estimate, which is P almost surely, so for almost every trajectory. And at the same time, you prove a bound when times goes to infinity for the term that appears here. And this bound, as I said before, depends exactly on the forcing terms that you have in your equation. And also this estimate is almost surely. Okay. So the idea now is to put together these two estimates. So if you put everything together, basically you are able to prove that the difference of U and V goes to 0 when times goes to infinity. So from the assumption we know that the mu has to be greater than this quantity here, strictly greater, so there exists an epsilon greater than 0 such that this inequality holds true. And so the idea again is to there's always the idea is to control this term here. So we write down this term here by adding and subtracting exactly the forcing terms, okay, and we split the analysis in these two pieces, okay. So when we take the limit when times goes to infinity of the exponential of the first term, of the second term here, basically we have that this limit goes to 0, since we have proved that when times goes to infinity, this term is less or equal than this quantity here, and so everything is less than 0, and so we have the limit of the exponential of minus constant times t, which converges to 0. And for the second term, we just use the assumption, so this term here is greater than 0, and so again the limit of the exponential is equal to 0. So basically, putting everything together, we just proved that the exponential of this quantity here goes to 0, And since this was the term that bounded the difference, we proved that the difference goes to zero. Okay, so in this way we basically prove that when times goes to infinity, the solution of the nudging system converges to the solution of the original system, and the speed of convergence is exponential in time. So more or less, this is the idea behind the proof. In the case of an additive noise, and somehow we generalize the results by as one also entity. So as you see from the proof, everything is, let's say, more quite simple in the sense that since you have an additive noise, when you consider the difference of the solution of U and V, the noise disappears. So all the estimates are pathwise, and all the reasoning is pathwise. When you consider the multiplicative noise, things are more delicate, since when you consider the difference, the noise does not disappear. So in this case, the analysis is more involved, and you have to consider estimates in expectation. So this is what actually, this is what we have done in the paper. So in the paper, actually, we consider the more general case of a multiplicative noise. So we consider the Navier-Stokes equation, but now the noise is of this form here. So you see that the operator G depends on the solution itself, so it is a multiplicative noise. And we work under different assumptions on the noise to see how well the algorithm is working. So we make the standard assumption of Lipschitz continuity for the operator G, and L will denote the Lipschitz constant. And here, just for simplicity, I will consider only two assumptions on the noise. So the simpler assumption is the case of a bounded noise. So G of U in the Hilbert-Schmidt norm, it is bounded by a constant, KB. And we can also consider the case of a noise that has a linear growth. So in this case, the assumption made on the noise is as follows. So the Hilbert-Schmidt norm of the operator G of U is bounded by KL, so a positive constant, plus K tilde L times U. Okay, so basically KL represents the intensity of the additive part of the noise, and KL tilde the intensity of the multiplicative part of the noise, and we suppose that the growth of the noise is linear. Okay, so we have different results according to the kind of assumption we consider on the noise, but also in this case, the idea is to try to understand how good is the approximation of the solution U in terms of this nudging equation V. So also in this case, we introduce the same modification. Okay, so we perturb the equation by the same control somehow. And this is what we proved. So we have, as I said, different results according to the assumption that we make on the noise. So if we consider a noise which is bounded, we prove that the solution of the nudging equation converges to the solution of the Navier-Stokes equation exponentially fast, but in this case we just have the convergence in expectation. And this is related to what I said before. So when you consider the difference of the solution U and the solution V, the noise does not disappear since it's multiplicative. So you have to deal with the difference of the noises somehow. And so in order to make the noise disappear, somehow you have to take the expectation. So in this case, the results are weaker since we are not able to prove a pathwise convergence. We are just able to prove a convergence in expectation. But what you can prove is that if the noise is bounded, then you have still an exponential decay. And the assumption that you make on the parameters, it's very similar to the assumptions that you make in the case of an additive noise. So also in this case, mu has to be greater than the intensity of the deterministic forcing, intensity of the additive noise of the stochastic forcing, and here you have to consider somehow the Lipschitz condition, the Lipschitz constant in the Lipschitz condition. What is interesting to see is that if you relax the assumption on the noise, so for instance, you consider a noise which has a linear growth, then the convergence is you have still convergence to zero, but is weaker. Since in this case you have convergence in expectation, but now you have a decayment which is polynomial, so it's slower in this case. And the power of the polynomial is related to the parameters of the equation. So in particular, to the viscosity coefficient, the domain, and the intensity of the multiplicative part of the noise. In this case, you also have stronger conditions on the parameter. So in particular, in this case, you also need to impose a large viscosity assumption in order to obtain the result. So in this case, you have to impose that the viscosity parameter is stronger than the multiplicative part of the noise. And also the condition on mu is related to this fact. So here you have again mu greater than the deterministic forcing additive part of the multiplicative noise. And then you see that this term here appears, so somehow it is involved also the multiplicative part of the noise, and under this assumption in particular this term is positive and everything is making sense. So I will give not an idea of the proof of this result, but I wanted just to emphasize that the speed of convergence that you obtain changes according to the kind of assumption that you're making on your noise. So just to conclude, I will just want to make some remarks. The first remark is more related to the deterministic setting. So somehow, let's say, this kind of result for data assimilation are not new in the sense that they are strongly related to the so-called Fourier-Prodi estimates that you have for the Navier-Stokes equation. So in a very old paper, Fourier and Prodi proved basically that dissipative PDEs, in particular the two-dimensional Navier-Stokes equations, possesses finite numbers of the determining parameters, such as low modes, for instance, but also, let's say, nodes and local spatial averages, as in our case. And these finite numbers of determining parameters govern the long time behavior of the equation. So what they prove in their paper is that if you consider two solutions of the Navier-Stokes equation starting from two different initial data, and you have that on the low modes, they agree, so on a finite number of directions, then actually when times goes to infinity, the two solution converges. So basically the dynamics is governed but by what happened on these finite dimensional manifolds. So the low modes determine the long time dynamics of the equation. And this is the idea behind the data assimilation, because as we've seen, finitely many observables basically determine the dynamics of the whole system when times goes to infinity. And this is exactly the idea behind the algorithm, because you are introducing this term here, and the effect of this term is to enforce agreement at the level of coarse observables. And let's say the dissipation given by the Laplacian makes the rest. So it's enough to prove that the whole solution converge one to the other when times goes to infinity. And in the stochastic setting, you have basically the same idea. So roughly speaking, when we prove our results for the data simulation, we basically used the same technique that you use to prove uniqueness of the invariant measure in the so-called hypoelliptic setting. So there are a lot of papers concerning this kind of studies. So the idea is that to prove uniqueness of the invariant measure, it is enough for the noise to act on a sufficiently large number of directions, because it is enough to stabilize this unstable manifold, let's say, and then the dissipation of the Laplacian allows you to prove the convergence, let's say, when times goes to infinity. So I just want to conclude by saying that somehow this is nothing new, in the sense that we use exactly the same technique that we use to prove uniqueness of the invariant measure in the hypoelliptic setting, and somehow the results that we obtain is just to let people know somehow that when you want to address problem of data assimilation, the technique that you use are very similar to the techniques that you can use to prove ergodic results. And with this, I conclude. Thank you for your attention.
So thank you very much for your nice talk. Are there any questions or comments? You can just unmute yourself and ask. So I have a question. Actually, two questions. So do you assume something on the range of G?
On the range, no.
No, okay.
No.
Okay.
No.
Second question, about the V0,
Yes.
the initial datum, which is arbitrary, right?
Yes.
So it only affects the constant, correct?
Sorry, it only affects?
In the convergence, it only affects the constant in front of the exponential. Is that correct?
Yeah,
what?
excellent. So it affects basically, you see here. So yeah, it's a constant. Yeah.
So if you don't know U0, then your best guess, V0, makes it better if it's close to U0, right? And then, so this is basically just a constant. Okay, and that's the role of V0. But it works for any V0, it can just be a very large constant.
Yeah, exactly.
Okay, thank you. Are there any other questions?